Okay. Yeah. So we are live now. So entity to expected date. So the expected date you can think like the next week. Okay. Either next week or next to next week. In between them, it will be going to happen. Okay. More
Just
details.
before the final.
Not just before the final. So as I said, it can be either the next week or next to next week. One of them will be
That would be really fun,
there.
actually.
Uh, Syllabus, it's not decided yet. Okay. We do not have the info more on that. So as soon as I will get, okay, we will update you about that. Okay. Yeah. So let's start with week 9. So as I said, week 9 broadly has two topics. One is the word embedding, and the second is the attention mechanism. Okay. So we'll be starting with the first part of the week, that is word embedding. Okay.
Sir,
So yes.
sir, can you just spend 5 minutes on context vector? So that was used multiple times in this week. So can you just spend on context vector?
Yeah, I will discuss that. Okay, the context we basically decide based on the word embeddings. Okay, so it comes from that how our word embedding should be made. Okay, so don't worry, it will come in this part only.
Sir, in quiz also there were some questions on context vector. So I think that's also taught in a way in last week, but I could not grasp it. So that's why.
Context vector then there. Okay.
No, context length was discussed, had been asked in quiz. No, context length it is.
Yes, sir, context length. Sorry, context length. Yeah.
So as I told for the PYQ, we will be discussing them on Wednesday. Okay. So, but do you have the question number? Which question you are asking for?
Some three words one and four words one and five words one, which is the best context length for this. Like that it was.
Okay.
So I thought it should be middle, but the answer is I think five words, the longest one.
Um. Let's see. Training model, sag oscillation. This one.
Okay, sir, you can go ahead. I think
Mhm.
discuss midway.
Okay, so it was with respect to the RNN. Okay, okay, okay. Okay, so the question was mainly related to what should be the ideal context length so that our model can generalize over all the input sentences. Okay, yeah, answer is 5. Okay, it was mainly related to like how you should stack them together. See, remember the idea of padding that we discussed in the case of RNN? Why we do that?
We also discussed truncate, no?
Uh, yeah,
So
we also
method four will be ideal.
yeah, we discussed the truncation also, but truncation when we do like it's when it's a very long sequence. Okay, we do not have that much long sequence as of now, so we can do go ahead and do with the idea of padding. Oh, okay. So truncation is only done by when we have large sequence. Okay. So this question was mainly related to how we should pad them so that all of these three sentences can be together fed into our GPU for the word embedding. Okay. So as we have the longest frequency of 5, okay. So you will take that as a context length, okay? And whoever sentence which is less than the 5, okay, you will just pad them accordingly, okay?
So
And the
context vector comes after the last hidden output, right? That is sitting
context
in
vector
between.
is something different if you are asking for, okay? Context vector generally the terminologies that we use is with respect to the word embedding. What in the question was asked was for the context length, that was like the length of the timestamp or the number of tokens you should use. Context vector is something different. Like if I say one example for now, uh, cat sat on the mat. Okay, so where did the cat sit? It sat on the mat. Okay, so there's this context associated with the between cat and mat. Okay, so that's the how context vector we define. Okay. Now in the okay, I will start with the word embedding, then I will also discuss what the context vector it is. But technically in our course, I don't think so. We are going with the direction in which we have to take into the account of context vector, as specifically as we discussed in the DL course. Okay. Can the value of perplexity be greater than the size of vocabulary? No, right?
No.
No, right? I think it was discussed in the lecture also that it has the highest of size 1. Okay. So if you look at the lecture of that in which the author has discussed perplexity, okay, he has also talked about this. I remember it clearly that he also said that it cannot be greater than the size of vocabulary itself. I remember this question because I made it. Uh, yeah, so let's start with the word embedding. Uh, yeah,
Pulkit, if you
yes.
have some formulas related to this concept, can we keep it last? You can give the story first before going.
Yeah. See, word embedding, it's not, we are not specifically going into any formula or something. Okay. It's
Okay.
mostly just about the intuition and why we need it. Okay.
Okay.
And we won't be having any much formula for the word embedding. The one formula you can expect is the number of parameter calculation here. That's the maximum that we are going to have for the word embedding part.
Okay.
Okay.
Thank you.
And of course, why we need the word embedding, I hope the idea should be clear. Our machine does not understand the words like that we speak. Okay. What is happy, what is sad, what is good, what is bad. Okay. Our names like Kshitiz, Sneha, Pulkit, Satya. Okay. So these words are not understand by the machine learning models. So we of course need numbers. We need to convert them into numbers. Now, how can we convert them into number? Okay. So let's start with the very first thing that I have. Let's suppose I have these three names. Okay. Now, one way in which we can convert them into numbers is just I can just simply name them as 0, 1, 2. Similarly, I can, if I have more than 0, 1, 2, 3, 4 like that. Okay. What's the problem in this type of embedding? And I hope you must have studied this in MLP
We
that
have
it's
weight.
kind of like,
We have weight associated. It's like
okay.
Sneha is 2.
Hmm.
It's greater than Pulkit, greater than.
Yes, correct. Okay. So this type of embedding is generally made by ordinal encoder. Okay. And one very big problem in this case is that it obviously it creates an order. So it will create that Kshitij is smaller than Pulkit is smaller than Sneha. Okay. So that's why of course we cannot go with them. And we have just one number. Okay. So we do not just want to stick to a number. We can instead go with our multiple dimension vectors. Okay. So another embedding that you can think is I have, let's suppose this 0, 1, 0, 0, 0, 1. It's what kind of embedding is this?
One
One.
hot.
One hot. Okay, it's what you get using one hot encoder. Now, Can you tell me what will be the problem if we use one autoencoder?
Sparse.
Very good. Sparse. Anything else?
Space.
Yeah. I think you mean by the dimension, like it's going to explode if you have more categories, right?
Yeah, yeah, space. It takes much space.
Okay, these are very good point, and at least I expect these two to you guys to know, because you guys must have done the MLP, or even if you do not, if you are doing it together, but by this time this topic was completed in MLP also. So these two, I hope you guys should know. The third fact that I had a problem with the one autoencoder is there's no context or similarity between the embeddings that you are getting here. Okay. So what does it mean by similarity here? Okay. Now let's suppose I have one embedding of man and I have one embedding of king, one embedding of woman, and one embedding of queen. Okay. What you will want is that the embedding of man and king should be like close compared to the embedding of man and woman. Okay. Like king is also a man. Okay. So the embedding of man and king should be closer if you compare the embedding of man and woman. Okay. And the notion of similarity, if we talk about in the case of vector, how do you check its similarity here? Or how do you check whether two vectors are close to each other?
Distance.
Yeah, distance is one metric. Okay. Now distance is very good, but
Being in the
generally,
same plane or something like that. Same plane.
see what we are going to stick to one rule here, that all of our embeddings are in same dimension. So that means if main is in R5, then king is also in R5. Okay. So chances of them to be in same plane, yes, it can be. Uh, but a good notion that we generally keep for checking the similarity between the vectors. Okay. That's like kind of a heart of the ML. Okay. Is the dot product. Okay. So it's going to be used quite a lot of time, the dot product that you check for the similarity. Okay. It's going to be used here. It's going to be used in the attention mechanism also. And in MLP, if you remember, you in the week 10, okay, the recommendation system, there also we discuss uh, dot product for the similarity case. If you have not completed it, you will be seeing it soon there. Okay. So dot product is much more used for similarity between vectors. Of course, distance also can be used. It's similar to what you will be doing in the neighbor algorithm. Okay. But dot product is much more feasible in terms of vector. Okay. So how the geometric intuition for this is, let me draw it in 2D for now, that if you have this vector of man here, then the vector of king should be here, kind of, while the vector of woman can be here. Okay. So if the dot product between two vectors are high, then in the space they will be closer to each other. Okay. Or basically the angle between them will be small compared to the dot product between two vector in which its value is low. Okay. So as the angle between man and woman is high, the dot product value between man and woman will be low compared to the dot product value between the man and the king, because their angle is small. Okay. Yeah. So till now, is it clear? Okay. Now, moving forward, so what can be the best way now to embed our words? So there are 2 or 3 methods more that you have studied in MLP. The count vectorizer, okay, and TF-IDF vectorizer, okay. Don't worry, we won't be using them in our course, but these are also some of the ways in which you can encode the words, okay. Of course, count vectorizer is very simple compared to the way in which TF-IDF works, okay. So I'll be taking the example of the TF-IDF way, okay. So the same example that we had, that cat sat on the mat, okay. So we do not just want to encode our words freely. We want them to have their encoding in such a way that they can represent meaningful context with the words in which they are appearing. Okay. So as cat sat on the mat. Okay. So there should be some context associated with uh, between the cat and the mat. Okay. So this type of context relationship we also want to capture. And another example, if I give, let's suppose the animal did not cross the street because it was too tired. Okay. So who was tired? The animal was tired. Okay. So the it has a context, or the it is referring to animal. Okay. So the embedding of these words should be done in such a way that this context relationship can be captured. Okay. So these type of things we want to make sure while doing the word embedding. Now there are some statistical more ways which are ways to do the word embeddings, but not discussed in our course. Okay. One of them is continuous bag-off model. Okay. In which you have your skip gram model. Okay. Now you will be seeing this in degree level DL course in the same week 9. Okay. In the same week, you will be seeing them in the degree level DL course. We have studied the what is continuous bag-off model. Okay. But in our course, we won't be having time to discuss this specifically. And instead, we will be going the neural network way of capturing the word embedding. That is just create the parameters for our word embedding and let it learn by backpropagation. Okay. So what does it mean? That for the vocabulary that we are going to create. Okay. Suppose our vocab has these words: cat sat on the mat. Suppose our vocabulary just has these 5 words. Okay. What I'm going to create, I'm going to first set how much dimension of embedding I want. That is, what is the embedding dimension I want for each of my words. Of course, it has to be same across all the words that I'm going to embed. So if I suppose if I let it to 3, let the dimension of embedding of word is 3. Okay. And what I'm going to do is I will going to have a matrix of order 5 cross 3. Okay. And I'm going to multiply it with each of my vector of each of my word here. Okay. And each of these embedding I'm going to start with some, okay, some random initialization I'm going to start with. And this multiplication is going to give me a 3-dimensional vector. Okay. So that's how I'm going to convert each of my words into the embedding dimension vector. Okay. Now, of course, why I have taken 5 here? Because I have 5 words here. In general, if your vocabulary of size V, okay, then it will have V such rows, and whatever the dimension you want for the output dimension, okay, that many columns you can take. Okay. And of course, the number of parameters
Can
that you are
you
going to learn is,
determine the dimension?
sorry.
How will you define or determine your dimension?
That's again an hyperparameter. Okay, you start with some, let's suppose like 64 or something. Okay, 30 to 64 you generally initialize with.
Okay, you
Okay,
just
or 100 to 100.
okay,
Again, it's an hyperparameter. Okay,
and it
and
learns, and then
learns
based
using
on the context given, it will or the vocabulary given,
yeah.
it has to decide
You
your
are just going to backpropagate through these embeddings also to update the parameters here.
and it will learn as long as
Yes,
you have
it
done
will learn.
it.
Yeah. Okay. So
So
that's
if you have a mixture of, say for example, multiple languages,
mm, multiple languages. Then see, for that we will be having different vocabulary. Okay.
okay, it has to
So
be
that's
separated.
more like a more hard problem than a simple one. Generally, if you are going to deal with a text corpus, then you generally have all the words of the same language only. Okay.
Because sometimes when we speak, we both mix our mother tongue with
Yeah.
English or something like
Yeah.
that, right?
So that nature is generally true, but that's usually handled by like some out of vocab words. Okay. So of course, it's not going to happen like you have a vocab and each of the new words that you are going to see has to be there in the vocabulary. Okay. So these things are handled by using out of vocab words. Okay. Now that you can handle using some tokens, special token you can create like the unknown token. Okay. Just like we create also our padding token. Okay. So just this is one way in which you can handle this. Okay.
Okay, in general, it is a hyperparameter, that is
Yes.
dimension is a hyperparameter.
Yeah.
And is there any upper limit?
No upper limit. It's
So
your
no
wish. Of
upper
course, you
limit.
cannot take it very large. Otherwise, things will get very high dimensional. Okay.
Okay.
Now, that's how it was used to done. Now, modern LLM like our GPT from OpenAI or BERT from Google. Okay. So the way the BERT works. Okay. So it's the model from Google. It reads your entire text document and then do the uh, contextual embedding of each words. Okay. Command. And then create embedding. Okay. So it's after going through the entire document, it then creates it. Okay. While we have GPT from OpenAI, okay, which basically do it in the left to right fashion. Okay. Now more on this we'll be studying in the week 10 where we discuss transformers in more details. Okay. At that point, these two will come again. Okay, and we'll be studying them their architecture in a little bit more detail than just this. Okay. But yeah, that's basically about word embeddings. Okay.
There is one more,
Yeah.
I forgot to ask this one. See, we here, this learning, how it happens, we do not have a label, right? Here.
Yeah. So what we have is the semi-supervised way. In this case, if you are wondering the left to right fashion, okay, what it's basically trying to predict is the autoregressive manner. That we have just this, let's suppose cat set
No,
on the
no,
map.
prediction is something else. Here we are embedding, right? We are giving,
Hmm.
we are saying it is going to understand the con, what what is the relation. It's like a man and a king. It has to put it in certain dimension so that the dot product is low, right?
Yeah.
How it does this one.
Which one? You mean the BERT one or the GPT one?
No, not
Okay.
this. Just I'm
General.
asking the very basic concept.
Okay. In
The
general, you are
previous,
saying.
yes, here.
So it's not like you will be start in the starting itself. You will be having things working out. Like in the starting, all the things will work out. That the man and king will be together while the woman will be different from the man. It's just that initially you will initialize with randomly. Okay. So you will assign a vector of random numbers to every word in your vocabulary. Okay. Then what you are going to do, you are going to train a neural network. Okay. So it can be like you are going to predict the next word. So given that you have just seen the cat and set, your goal is to predict that what should be the next word here. It should be on. Okay. So in this way, you already have your text corpus. You are going to create a
Okay.
label on your own based on the text sentence or the sequences you have.
So based on this, it pushes this.
Uh,
It
Step
creates embedding
accordingly.
for cat, and
Hmm.
then based on the future learning, also it changes that embedding
Yes.
by
Okay.
back
So it
propagation. That's
simultaneously adjusts the word embedding vector. Okay. Along with the other weights that you are going to have for your models. Okay. So we're going to back propagate through your embedding parameters also
so. This
to update
embedding
the
is
embedding.
it is like more like what do we call overfitting only, because once it sees everything, it is like just copying, and then it has some like a lookup kind of a thing.
Uh,
Once the model sees the entire vocabulary,
hmm.
it is like it has a lookup for everything, right?
See, if you have enough data, then it can generalize the things. Okay. In the case, if you have very small data set, then of course it can easily lead to overfitting case. And that usually happen for any neural network model because any deep learning models is hungry for the data set. They require huge amount of data set for them to perform well. Otherwise, they are going to just overfit on your small data set that you have. Okay. Yeah. So
And what about the languages which starts from right to left? Not all languages
yes, correct.
and top down.
Uh,
Some
so,
languages we write
hmm.
top down.
So we have another more type of tokenizer. We have BPE, that is byte piece encoding. We have then word piece, and then we have sentence piece. So if I remember correctly, then word piece and the sentence piece tokenizer are the one which are you know resistant to this left to right fashion. Like it doesn't matter to them that whether you read the sentence from left to right or right to left. Okay, they can be easily adapted to embed your words. Okay, but
Hmm.
of course this is out of the
These
syllabus.
are all libraries, is it?
These are all the tokenization way that our
Tokenization method. Okay. Okay.
yes.
We will
Okay,
do it there.
you will be basically studying them in LLM course. Okay, not in our DL course. So going to be in the LLM. Okay, or I don't know if it comes in the later part of the week, but so far we have not discussed it. It has not come till week 10. Not sure whether it's going to come in week 11 or week 12, but if not, then you are going to see them in LLM course in degree level. If you take it as it is an elective course. So,
Thank you.
okay. Yeah. So, any doubt in the word embedding part? Then the second topic of the week, that is the attention mechanism. Now, this is a very important topic because attention is what lead to our modern LLM basic architecture, that is the transformer. Through the paper, attention is all you need. That comes in, I think, 2016-17. Okay. So it's the main building block for our modern LLM, attention. Okay. Now, intuition behind using the attention mechanism is, let me going to write two sentences. The first one that I already wrote, that the animal did not cross the street because it was too tired. Okay. And let's suppose the second sentence is the animal did not cross the street because it was blocked. Okay. Now, what does it refers to in the first sentence?
Animal.
Animal. What about in the second?
Street.
Street. Okay. So there's this saying that the word is known by the company it keeps. Okay. So based on your sentence, okay, the meaning of the word or the its context, okay, it can be changed. Here, the it was referring to the animal, but the same it here, okay, refers to the street. So based on the company that your word keeps, its meaning changes. Okay, and so does intuition one make is its embedding also should change. In all the previous method that we discussed, okay, what we used to do is we used to fix the embedding for one word. That is, uh, the same embedding vector that I'm going to create it for my it. Okay, the same embedding vector will be used here, and the same embedding vector we're going to use here. But of course, if you are going to see it from as a human point of view, then both it here has a different meaning. Okay, and it's depending upon the words that it is carrying around with it. Okay, so that's where we are going to head now, the attention mechanism. Okay, so what it's going to do is, let me take one small example first, the cat one. Okay, for each word that we have, okay, I will not just going to take the embedding of these vectors as it is. What I'm going to do is I'm going to take some summation of each of these words, and just not the direct summation, of course. They will be weighted by some alpha quantity, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, let's suppose. Okay. And this entire summation I'm going to take. Of course, we are going to see how it's going to happen. Okay. So alpha I, and then let's suppose the embedding of this word on is Vi. Okay. V is the vector representing the on. Okay. And okay. So for now, let me keep it as V3, and I'm going to sum it from I equal to 1 to 5. Okay. And then this will be my embedding for on that I'm going to use. Okay. Now what it's basically doing is we are checking how much attention it should put to each of the words that are appearing with it. Of course, with itself also. Okay. So we are not only just focusing on uh, one word. Okay. We are focusing on each of the words with which it is going to appear. Okay. And how much it's going to focus on, these are weights by these alpha, which are basically called as the attention weights. Okay. Yeah. So
These weights are also learned.
yeah, of course, these weights are of course learned. Okay. Now,
This one will be having then lots of
of
parameters,
course,
right?
yeah, lots of parameters, of course. It's going to happen if you see in now the parameters that we have for any transformer models or LM models. Okay. It generally goes now in billions like that. Okay. So of course,
It
the
is
parameters are going to explode, but now we have the capacity to handle that much.
yeah. It is basically the capacity helps us to do all this rather than we call
Yeah.
it as model.
Okay.
It's just a look.
Yeah. So one more thing that will be more evident in the week 10, but if you see in the RNN, what we used to have this structure, right? The sequential structure in our RNN case, in which this recurrent connection that we are creating here, it this recurrent connection used to help us to connect with the past timestamps. Okay, but as this timestamps increase, okay, what used to happen? We used to have the problem of gradient vanishing. Okay. But if you see the same type of context thing, we are able to capture here using the attention mechanism that we are going to see in just few minutes later. Okay. And one good thing about this is it can be parallel. Okay. All the computation that we are going to do for this attention mechanism part, it can be done parallel. While for the RNN, it has to be done in the sequential manner. That means for this process to go forward, you need to wait until the process before it gets finished. Because once only you get the output of this, then only you can feed it as an input to the next one, and then only you can proceed further. Okay. But what
Why
we
they
have,
did not design something like this Google Net for RNN? For convolution, they did Google Net wherein you do parallel things, right?
yeah, there it was the idea was different. Uh,
No,
was
it
to
is
select
CNN
multiple.
is CNN is serial, right? But Google Net just put all these things parallelly,
Is
and then
there's a little bit difference between the serialization here. Okay, 1 minute. Give me 1 minute. Is it okay now? Okay. Yeah. So my headphone battery got died. Hmm. Yeah. So about the parallel thing and the sequential thing, the main problem in the RNN was that we already had our entire sentence. Okay. So this cat sat on the mat. Okay. This entire sentence we already had in our hand, but it was due to the design of the RNN. Okay. We had to do this entire work sequentially, even though this entire sentence we already had in our hand. Okay. So this sequential task was just because of the design of the RNN. Okay. So this what we wanted to do in the parallel way, because we already had all our words and all the entire sentence. Okay. That's because the architecture design of RNN was that everything has to be done in the sequential manner. Okay. So we have to wait here until the previous task was done. This task was later done parallelly using the our attention design that we have. Okay. Now about the inception model that you are talking about in the Google Net architecture, in that if you say that they just made one thing there, that they used multiple different size of convolution uh, layers to get different kind of feature representation and just take them together. Okay. Still the entire network was still in the sequential manner, and that happened for everything, for your simple ANN case, for your simple CNN case. Okay. And even your transformer that you are going to see, we still have this sequential connection, but the main thing that became parallel was this, the attention mechanism part. Okay. That was earlier sequential due to the structure of the RNN that we had. Okay. Is it clear?
yes, yes.
Okay. Yeah. So this was the part that only became parallel. Other things is still going to remain sequential, and once we see transformers in the next week, then it will be much more clear how this entire attention block works. Okay. So yeah, Now let's move towards how we are going to uh, compute these alpha i's that we have and all. Okay. So first, before that, I have to define few terms. That is query, key, and value. Okay. So what does this they mean? Okay. So we have one word for which we want to do the query. Okay. So this is the word for which you want to compare. Okay. And key is basically all the words that are available there. Okay. So what does this mean basically? Uh, for the on, okay, if I want to do this attention mechanism part for my word on, then on will be my query. Okay. And I'm going to look it for cat, then first cat, then sat, then with on itself, then the mat. Okay. So cat sat on the mat, these will become key. So on will become my query, and let it be represented by q1. Then cat will be my key 1, sat will be my key 2, key 3, key 4, key 5. Okay. So it will be like the pair. Okay. Query key pair q1 k1. Okay. q1 k2, q1 k3, like that. Okay. So like that this pair will be made. Okay. So more formally, let me write it. uh, it's like who should I pay attention to. Okay. uh, so it's my current word, that is my on. It is asking like for which word should I pay attention to. So should I pay attention to cat, or like more formally it should be like how much should I pay attention to cat, how much should I pay attention to sat, how much should I pay attention to myself, to the, to mat, etc. Okay. Key is basically the word itself. So the word I am. Okay. And value is basically what they offer. Okay. So the v that I have taken here, okay, it's basically the value of the word on. Okay. Now of course this query key and value, it's not directly like our word embedding. We are going to first of all create uh, this query key and value pair. Okay. How we do that? Same funda like before. We are going to create the matrix. Okay. And using that matrix, we will be having a matrix for query vectors, we will be having a matrix for key vectors, we will be having one matrix for value vectors. Okay. So to make you guys understand these things, I'm going to take one example. um, Give me 1 minute. Okay, so I'll be starting with the numerical example, and using that I'm going to explain how this entire things work. Mm, Okay, so do not read the text as much. Okay, uh, just focus on small things. Okay, yeah. So main thing to focus here is that we have given this our initial embeddings. Okay, so we have d equal to 4. Okay, this is a matrix of, let's suppose, t cross t. Okay, we have these three words x1, x2, x3. Each of its dimension is 4, so that's why d here is 4. So our embedding dimension here is 4. We have three tokens or three words here. Okay, then how this attention mechanism is going to work? You will be having, as I said, three different matrices: one for the query, one for the key, one for the value. Okay, so WQ, WK, WV. Okay, now how their dimension is going to match? Okay, as uh, okay, so as we have three words. Okay, what we want is we want the query vectors for all the three words. Okay, so as even though like it's written here, how this operation is going to happen. So x is of dimension t cross t. Okay, so my WQ should have dimension d. Okay, that should match the dimension of my embedding of my word, and then it will have something called as, you can say, d had, or sometimes it's also called as dk. Okay, this is basically just a notation for denoting the dimension of my query vector or key vector or value vector. Okay, in the paper, attention is all you need. They have kept the dimension of query key and value vector as same. Okay, and it's usually denoted by d had or dk. Okay, it's just a notation. You will understand the importance of d had more in when we are going to study the transformer architecture. Okay, but for now, if you just want, then you can think like the row should match with the dimension embedding. Okay, and it's just that what dimension in which you want your query key and value vector to be. Okay,
No,
yeah,
I'm not able to understand this query key and value vector. Why it is 4 cross 4?
yeah. So see, it has four because we want to do this projections here. Okay, 1 minute. Yeah, see, what we want to do is we want to do this multiplication here. Okay, we want to get the query embeddings, we want to get the key embeddings, we want to get the value embeddings. Okay, as we want to learn different representation for based on how the words are appearing together. Okay, so that's why we will be going to have these matrices to know or to learn about the query key and value pair for each of my word embedding that we have. Okay, so I have my word embedding in R4 as the dimension of my word is 4. That's why if I'm going to multiply them in such this way, x w q, okay, it should have 4 rows at least. Okay, now of course the second part, that is how much column it should have, that's again up to you how you want to decide. It's again in hyperparameter, and it will going to basically have the dimension of my query vector. Okay, is it
Query vector means in this case, if we take only on, then it
yeah?
is full.
So in this case, if we are going to take on, then it will have the query vector
But
in
the
R.
dimension will be 1.
No, 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 dimension will not be 1, it will be in 4, right?
Oh, okay, on has 4. Okay.
Yeah,
4.
because it's output in 4, right? If you do this operation, then x, you will get output as d times the number of columns it has. Okay, so t is basically the number of words you have. Okay, and for each of words, you are going to get a query vector. So q1, q2, and q3. Okay, so for this case, you will be having 3 cross 4 matrix. This q that you are going to get here will be 3 cross 4 matrix, as you have 3 words here. Okay, and the output dimension of your query matrix is
4. So that's why 4. Okay. Now, is it clear till now? So far, we are just learning how we are going to get our query vector, key vector, and value vector. Okay, we have not gone till this part, like how you are going to learn this weightage score that we are talking about here, that how much attention should I pay to this vector and how much attention should I pay to this vector and all. Okay, so that
Now,
part.
first we need to get an intuition of what is this projection.
Yeah, so these
Because
are
you
just
say projection matrix, right?
see, yeah, these are just projection matrix. We are just projecting our embedding dimension vector to the query dimension vector. Okay, of course, every matrix multiplication that you are doing is technically a projection here. Okay, from some dimension D to some other dimension K. Okay, as here both of them are same, but if let's suppose your embedding dimension would be like 50, okay, and your query dimension is let's suppose 16, then what you are doing from your 50 dimensional embedding vector, you are projecting it on 16 dimensional query vector. Okay,
Okay.
so you are going to get a query vector, a key vector, and value vector. Why we need them? So that we can compare the query and key vector, as I said here, that for on, if I'm querying about, and I will ask for each of my word, okay, that are available in my sentence. So cat, sat, on, the, mat. Like this is what we are doing. We are basically asking how much should I pay attention to? How much on or how much this query vector should pay attention to cat, should pay attention to sat, on, the, and mat. Okay, that's what I am asking here. Okay, and we are not just directly using the word embeddings that we have. Okay, we are projecting into 3 different dimensions. Okay, query, key, and value. And for each of word, I will have a query vector, key vector, and value vector. First, I'm going to compare my query and key vector. Okay, on is called the query, and this cat set on the mat. Okay, these will be my keys now. Okay, so far is it clear?
For that, how this projection helps?
See, this projection is to get the embedding for your query vector and key vector. Okay, just like what you did earlier, you had your word.
Now, I will put my question differently.
Yeah, okay,
Here, all my projections are in
R4.
R4,
Yeah,
and my embedding is also in R4.
yes, correct.
So my query vector, key vector, and this value vector is R4 again.
Yeah,
So if I project how different numbers are coming, my embedding projecting to any R4,
hmm.
how if it is a query vector, it is a different numbers.
Yeah. See,
Key vector,
both of
how
them are different metrics, right? So of course, after projecting, you are going to get a different vector for both of them. For query key and vector for the same word, we are going to get a different query vector, a different value
oh, it
vector,
is
and
on
different.
that word. Okay.
Okay. So let me do one multiplication. Let's suppose I think then it will be much clear. So I have this access. It's lagging a little bit. 1010. 0110. 1101. Okay, so I have this is my x1, x2, and x3. Okay, so let me just take x1. Okay, for simplicity, I'm just going to take one vector 1010. Okay, I have my q matrix, wq matrix, that is my query projection matrix. So it will be x1 wq. So my wq is this 1001. 0 1 1 0. One zero one zero 0 1 0. Okay, so this was my WQ matrix. My x1 is this 1 0 1 0. Okay, if I'm going to multiply this, okay, just do it. So you will get 2 0 1 1. Okay, so this is my query vector 1 q1. Okay, similarly if I multiply my second x2 here 0 1 1 0, and I'm going to get q2 and q3. Okay, so this was for the query part. Similarly I can have my wk matrix also to get my key embeddings or key vectors. Okay, and of course you are going to have different matrix, so you are going to get a different key vector representation, a different value representation for the same word embedding. So it's kind of like if for one word embedding you are going to get three different vector representation. One we are calling it as uh, query, one we are calling it as key, one we are calling it as a value. Okay, intention behind using him, we are going to make use of first query and key vector. Okay, to see how much attention one word should pay to other words. Okay, and using that we are going to get something called as attention weights. Okay, how does read.ai uh, so using that we are going to get alpha I for each of them. These are called the attention weight. We will be seeing them how you are going to get. Once you got these attention weights, we are going to do this weighted summation to get the final embedding. Okay, yeah.
Here in this vector, you have written 2 0 1 1, the last one.
Yeah,
Uh, can we say that if the sentence is cat sat on the, then on should pay two times weight to cat,
no no no
like that?
no no no,
Okay, it is not
this is
like
not
that.
the attention weights now. Okay, it's just the query vector that you have. Okay.
Okay, with the help of this, we are going to get that.
Okay, yeah. With the help of them, we are going to get attention weights. Okay. So attention weights is similar to like we are going to get as we are going into the weightage part. Okay, so let's discuss that now. How should our properties of attention weight should look? Okay, that's basically our next topic now. So, properties of attention weights. So how should they be? Should they be like all the non-negative weights? Okay, and should they be like hard attention kind of thing? So it's like one word should only pay attention to one word and not other. So it's like 1 0 case, or should they be like probabilities? Uh, should they be like probabilistic way, or should they be like average pooling way? Like you should treat all of them equally. Okay, so of course there are different ways. Okay, in which you can do this attention weighting. Okay, the one way in which we are going to go with is kind of probabilistic way. Okay, and in that we are specifically going to deal with the softmax way. Okay, so we will be applying softmax in the final output to get the attention weights in the probabilistic distribution. So in that what we are going to get basically like if we are going to get final attention weights as like point 0.2, zero point 0.3, zero point 0.4, okay, 437 to 9.1. Okay, we should have one more. Okay, so it will be like on will pay 10% attention to cat, 10% attention to sat. Okay, so that we can treat them like that. Okay, that's our next focus is. Okay, so using the query key vector, the way we go ahead with this is we do the dot product again for the similarity. Okay, as you want to see how much my vector query vector should pay attention to my this key vector, So it's again the case of similarity. So again, we will be going with the dot product manner. Okay, now this is one type of attention in which we go with the dot product. Okay, this type of attention is basically called as scaled dot product attention. There's different one also that's called as bandhanu attention. Okay, that we'll be seeing in the implementation case of this takeaway. In the implementation part, we will be seeing the bandhanu attention, but in the theory part, we'll be seeing the scale dot product attention because that's what it is used in the transformer architecture also. That's we are going to see in next week. Okay, so but once you understand one attention weight, it's just some equations will different. Otherwise, the intuition will be the same. Okay, so in this scaled dot product attention, we will be doing the dot product of each of my query vector with the key vectors that I am going to have. So Q1, Q2, so Q1 with K4, Q1 with K5. Okay, so that's what we are going to do now. 1 minute. So let me see. This is I have query one vector, and notice my only key vector is changing. Okay, so we can treat it like alpha 1 1, alpha 1 2, alpha 1 3, alpha 1 4, alpha 1 5. Okay, so this is the attention weight for my first vector. Okay, or my first query vector on the first key vector. Attention weight for my first query vector on the second key vector, and similarly like that. Now this was of course for the query 1 or the first query vector. Similarly you can have for q2 also, q2 k1, q2 k2, q3 k3, and like that. Okay, so this will be denoted as alpha 2 1, alpha 2 2, alpha 2 3, and so on. Okay, so for each of my query word, I'm going to first take the dot product with respect to each of my query word embedding. With that, I'm going to get this code. Okay, how we are getting this? This is just the dot product between these two vectors. So I'm going to get one query vector, key vector, just simple dot product. I'm going to get this value. Of course, this is going to be a scalar value. Okay, once you get these scalar values, okay, what you are going to do is you are going to apply softmax on this. Okay, because this is unnormalized form, you want the probabilistic way, so on these value you are going to apply the softmax. Okay, so then you are going to get a probabilistic way. So for example, alpha 1 1 divided e power alpha 1 1 divided by e power alpha 1 1 plus alpha 1 2, alpha 1 3, alpha 1 4, and alpha 1 5. Okay, so this after applying softmax is what I am going to have called as the attention weight. Okay, so is it clear till now? If not, then what's the out here?
What about the value vector?
Yeah, value will come here. Okay, till now what we have calculated is the attention weights. Okay, value will have role here. Okay, so it will be just the attention weights that you have multiplied. Okay, the weighted sum of them will be your value vector. Okay, so with respect to each attention weights that you have, okay, you are going to multiply it with the value vector that you have. Okay, so
No, it's too complicated to.
yeah, so
Because why they have this many parameters? First, we need to understand why they are doing this. Why these three vectors? What part it plays in this model understanding? Whatever we are talking about, this attention as well as the embedding, right?
mm.
These two are the
See,
one
embedding is
which you know.
And then
model tries to use and then uh, uh, help us, right, when we ask a question. So why these two are important? Embedding, we say it is learning something, the relationship, correct?
mm,
Okay, and then coming to this attention,
yes,
where it helps.
yeah.
Why
So
on should be having an attention on cat and sat on there on the mat, and how it helps for the LLM to reply us.
yeah. So the first part that I started with here is basically gives your answer. Okay. So in the word embedding, okay, as I said, in the first sentence here, the it was referring to animal. In the second sentence, it was referring to street. So word is known by the company it keeps. Okay. Depending upon the sentence and the word it is coming with, okay, your focus or the attention that you should put is going to change. Okay. In the first part, it was referring to animal. So it was focusing on more on animal than any other words in this case. Okay. In the second one, it was referring to street. So it has more focus or attention on this part. Okay.
Basically, this attention helps the LLM to understand the grammar.
You can think of it like that, that it helps them understand the context that we have. Okay. How much focus one word put on the other words, and
Basically, this is
using
what
that.
in our English class that the English teacher teaches.
Yeah.
This
So
it
it,
means street.
yeah.
Here it means animal.
So using that, it's going to get more focused on the attention part. Okay, how much each word should pay attention to other words. Okay, and based on that, how its meaning and different representation you are going to get. Okay, and for that we are going with this query key and value parametric way, in which first we get the query and key vector. Okay, using the query and key vector combination, you get what is called as the attention weights. Okay, this attention weights basically refers like how much my one word for which I'm querying about should pay attention to the other words that we have in our corpus or the sentence. Okay, once you
Here,
get,
one vector itself is not enough. Only this query vector is not enough to learn the attention. Why key is necessary?
yeah, sorry, I think I left by mistake. Yeah, so see, one query will not be enough here. Okay, any external mm, one
Because
that.
already these are different numbers, right?
Mm,
Cat has a different query vector. Sat has a different query vector. On has a different one. There, mat.
mm.
So multiplying that itself, it cannot learn. It needs a key vector also.
Yeah, so see, using the key vector, what we are doing is we are getting the similarity score here. Okay, how much on should pay attention to each of these words. So we have the query vector and the key vector there. Okay, so these two are different vectors. Okay, if you are going to keep it same, then always what you are going to have, you are going when you are going to do the uh, dot product of on, let's suppose. So my query vector is on, key vector is also on, and you are saying if you are going to keep it same, and for this one you are always going to get what, highest, right? Because both of the vector are technique same. So for on, you are, or basically the word for which you are querying about, you are always going to get the same or the highest attention weight for that only. Okay.
Finally, we are doing softmax now.
Yeah, finally we are doing softmax for the normalization case, so that we get a
Okay.
probabilistic view kind of.
No, but for that we can leave, right? On to on, we don't need to. We can make that also. Because
uh,
normally we can reduce one calculation also. We don't need to get the attention of the same word to itself, which is logical. because in grammar you will not have, right?
But it
Because
is.
I'm just trying to understand why we need to separate vectors, because the query vector for each of these words are different.
Hmm.
That itself, when I dot product the query vector of on to the
Hmm.
query vector of cat, will it not sufficient and the model can learn only with that? It needs a key vector also.
Okay,
That
so
is it. Because
here,
on to on you don't need to do same to same, right? We can just drop it off. One calculation you can drop. No, I'm just asking.
Mhm.
Maybe we can proceed. Maybe we can discuss it in another session also. Can
Okay,
take it as a question and then we can think about it. And
okay. We will come to that part. Uh, yeah. So till now, whatever we got was the softmax. After playing softmax, we got the attention weights. Okay. So even though like this is kind of like a abuse of notation here, that I'm representing alpha 1 1 also as the unnormalized attention weight, and also the after playing softmax also as a attention weight. Okay. But uh, suppose that alpha 1 1, alpha 1 2, and all. Okay, these are the attention weights that you got after applying softmax. Okay, then after that, what you are going to do is alpha 1 I times vi summation from I equal to 1 to whatever your timestamp you have. Okay, so you have this alpha 1 1. Okay, then you are going to have your value vector 1, alpha 1 2, value vector 2, alpha 1 3, value vector 3. You're just going to add them, and this is what you are going to get as the final attention output. Okay, for my first word. Okay, so as it is keeping, like for this my value vector, how much attention it is keeping. For this my second value vector, how much attention it is keeping. And for this my third value vector, how much attention it is should keep with respect to the first word for which I am querying about. Okay, and this will be the weighted sum of this. That will be my final output. Okay, now this process is going to repeat for like all of your words. Like for as you have three words here in our example, so you'll be having alpha 2 1, alpha 2 2, alpha 2 3 also, then alpha 3 1, alpha 3 2, and alpha 3 3 also. Okay, and that's how the attention mechanism is done.
Do we have parameter calculation in attention mechanism this week?
uh, I think yes. Then if yes, mostly it's related to the WQ, WK, and WB matrix only. Okay, so for example, for the WQ, as it is a 4 cross 4 matrix, so 16 parameter from here, 16 from here, 16 from here, so 48 parameters. Okay, that's all we have. Now, one factor here that I have left in between, that was the scaling factor of square root of dk. But for that, I have to come to this the matrix way of doing this. Okay, till now whatever I explained was kind of like we are going with one vector at a time. Okay, but of course in the PyTorch or TensorFlow, these things are not going to happen in like for loop kind of way. Okay, all of these things are going to get vectorized. Okay, so here, as after the product. Okay, after the product of query matrix, key matrix, and value matrix, you are getting this qk and v, right? So these qkv matrix we are going to use to parallelize this entire computation. How we are going to do that? What was the first thing that we started with? We did the dot product. So we are doing the dot product of this qk transpose. Okay, q was a for the what? T cross dk. Dk I am representing is the dimension of query or key. Okay, this was also of dimension t cross dk, but of course once you do the transpose, it will become the dimension of uh, dk cross t.
Always all this q, k, and v weight matrices will be of same dimension.
This was done in the original attention paper that they took it in the same dimension. One thing that for the query and key, there has to be in the same dimension because we are doing with this dot product way, right? So if you want the dot product, they has to be in the same dimension. For
Yeah.
value, it's your choice whether you want them in the same dimension or not. But in the first transformer paper, that was attention is all you need. They kept it all of three of them as the same dimension. Okay. But for the value, it need not to be. You can choose it to be a different dimension also. But query and key has to be the same dimension
If
because of the
value changes, then alpha also changes accordingly, no?
if value embedding dimension changes, then alpha changes accordingly. See, alpha here that you are getting is a scalar. V here is a vector.
Alpha 1 1, alpha 1 2, and alpha 1 3 will be a vector, no?
No, no, no. Alpha 1 1 is a scalar. Alpha 1 1 was the output of
Altogether, I'm asking. Altogether, you will be having a linear combination with the values, no?
yeah. Alpha 1 1 here was the scalar. The vector was this V vector. V1, V2, V3. They were the vector.
Okay.
Okay. Alpha 1 1 was the output of dot product between Q1, that was my first query vector, with K1, that was my first key vector.
Okay. Okay.
Okay. And then for here we kept the Q as a constant and we are only varying about K. Okay. So
So
this
this, if we take on Q3 and K3 will not be same, but they will be similar.
Q3 and K3.
If we take on, no, a cat sat on, if we take the third position on,
Hmm,
so query vector and key vector for that on will not be same, but
yes.
similar.
Yeah, they will be of same dimension, but not the same.
Okay.
Okay. Dimension would be same, but they will not be uh, same vector. Okay.
So this is what we want to understand the intuition. How this is, how they are doing this. As
In the Bandhanu attention mechanism, that was the first time attention was used. In that, they did not go with this method of like taking with query key and value vector. But in the transformer paper, they decided to go with this and this worked. And
yeah, there should be some reason for doing this, right? That is there. That is what we want to understand. There is a
so
reason. This is just an empirical way. They tried, tested, and then went to this. Maybe they started with something and then they come to this during the from the inception to the level what we are currently, right? So we just want to understand how this has come and why three vectors are necessary, because this is a model and it is going to learn. It can learn with lesser, fewer parameters, right? We that is what we all want.
okay.
That's what.
Uh, okay. So for the less parameter, see the more parameter, of course, your model is going to perform well. But here, if we talked about 10, stick to one vector only.
Maybe during the from the starting of this type of a modeling, maybe they started with one and then something happened, like we did CNN and then the other types, right? Types of models. How we started from there, how we came, and then what are all the reasons behind. Maybe that kind of article is there. Maybe that would help to understand straight away. Okay, we for the same word, I need to have three vectors just to understand this attention. Attention is only one thing.
Yeah, but attention will going to differ based
I
on the
need three
different.
things to determine this one thing.
Two vectors are used to get the score, and then finally you are using the third one to get a linear combination of like how much weight you should put to one word at a time. So that's the current intuition that I had. More than
Yeah.
that, if you want one visualization was there by 3B, 1B, 3 blue, 1 brown. There was one visualization I think they had for the LLM attention mechanism. That video you can check it out if you want.
Yeah. Yeah. Let
Okay,
me see.
and other one resources if you want. Then the paper itself in which they introduced this, the attention is all you need. You can easily find it on the web. Okay, so you can also read through that paper if you want. Okay, yeah. So the final part that we were coming. Okay, to make this entire calculation parallel, okay, we have to go with the vectorized method. So the first part that we are doing is the dot product way. Okay, so we will do the dot product of these matrices in such way q k transpose. So q was the order of t times dk. Dk is the dimension of my query or key. Both of them should be at the same dimension because you are doing the dot product, so they has to be the same dimension. K was also of dimension t cross dk. Transposing it becomes the dimension of dk cross t. Okay, then of course you are going to apply softmax on this. Okay, now to account for numerical stability and to make the invariant, we scale it by dk factor, square root of dk. Okay, dk was the dimension of my query or key. Okay, so you divide this entire computation or this entire scoring that you are going to get after the dot product by square root of dk. Okay, this is to handle the variance part and the computation part. Okay, and then we will apply the softmax, and still the entire thing is our shape t cross t. Okay, and finally you are going to multiply it with v, which is of matrix t cross dv. Dv is the dimension of my value vector. So the final output you are going to get is of t cross dv. Now dv can be keep of different dimension than my query and key dimension. Okay, but in the starting paper they kept all three of them the same, and most likely in our course throughout the time most likely we'll be keeping it same only. Okay? But it can be keep of different dimension that you can remember. Okay, so this is how you can make the entire calculation here parallel by using the vectorized form of this. Okay, so yeah, that's all was there in the attention mechanism. I think more intuition for this will become stronger when we will go with the next week where it was actually used in the transformer. And it's will be a little bit more complicated because there will be 2 3 types of attention. uh, Technically there will be 3. Okay, one is
So we
the
we talked about self attention, then there will be cross attention. Then what is the third type?
masked attention.
Mask.
Okay, and the third one is masked one. Okay, so the self attention is basically done in the encoder part. Remember the encoder decoder architecture that we studied in week 8? Okay, so in the encoder part we do the self attention. What does it mean by self attention? Just like the example that I took here. Okay, we are checking the attention of my sentence with itself, the word of my sentence with itself. So this is my sentence that of course I'm going to feed it to an encoder. Let's suppose I'm doing the translation work in the translating into different language. Then here the example that I initially gave, that I'm checking the attention for my on with respect to all other weights. Okay, so this is the self attention. Okay, the cross attention that we have. Okay, this is for when we do the attention between encoder and decoder block. Okay, from the decoder when I'm translating my sentence, okay, then I will take I think query comes from the decoder and the key and value will come from the encoder part. Okay, so that's the cross attention. It happens between encoder and the decoder. Okay, now of course this will be much more clear in the next week. Okay, and the decoder also we have this masked attention. Okay, now why it is called as the masked attention? Because in the decoder we won't also want to do this parallel thing that we are doing in the encoder. Okay, and to make it parallel we have to mask it, but whether we have discussed the mask concept here. Okay, sir has discussed it, but okay, so let me just quickly tell what was the reason for the masking here or why we need it. So this encoder decoder architecture that we had, encoder and the decoder. Okay, in the encoder we can make this entire thing parallel. Instead of going with the RNN way of doing the sequential, we can make it parallel like this. Okay, but in the decoder we cannot do the same thing unless we play around with some tricks. That was the mask trick that we use, because if you do the same thing that we were doing in the encoder, that like you feed the entire sentence. Okay, in the encoder part it is fine, but decoder is the part that does the prediction for us. Okay, so in the decoder, let's suppose the translation of this in some other language you have. Okay, if you are going to feed this entire thing at one at a time, okay, entire thing at a time, okay, then it will be like your decoder has already seen the uh, next tokens already. Okay, so in that way it's not going to able to learn to predict the next token. Okay, and to prevent my decoder to not able to see the next words, okay, so that it the prediction happens in the autoregressive case, like we fed in through one word, then it predicts one word. Okay, then kind of like the next word goes in and then it's going to get predicted. Okay, like the teacher forcing way that we did it earlier. Okay, to be able to do that we go ahead with this masked attention, in which what we do is we basically okay, kind of mask my future tokens. Okay, how we are able to do that? It's a clever trick that they did in the softmax calculation part. Okay, remember how the softmax calculation works? It e power something you have, okay, divided by the summation of e's, whatever you had here. Okay, now tell me what will be the value of e power negative infinity?
0.
0. Okay, so that's basically what they did here. They created called as the masked matrix, in which what they keep is uh, you will have word 0. Okay, let's suppose I have 5 tokens in my decoder. Okay, that means in the translation I will be having 5 words. So 1, 2, 3, 4, 5. So in the first, when I'm predicting the first word, I only want that my first word should be there and other words should be masked. So I will keep this as
So it
negative.
would be a lower triangular matrix basically. You're saying.
Yes, kind of like that. Okay. Okay. In the second word, I only want my first and second word to be appear and the rest word to be masked. And then in the third time, like this. Fourth time, like this. Fifth time, I can see all of my previous words. Okay. So at whichever token position I am, I can only see that word and the previous word to it, but I cannot see the next word. Okay. So they created this masked matrix, and in this softmax calculation that they had, okay, they did this part, softmax of qk transpose by square root of dk plus m. Okay, now what will going to happen when you are going to add this to this? Okay, as it is 0, okay, so nothing is going to happen, but when you add minus infinity, Okay, the attention weight for that will become 0. Okay, so you have reduced or you have masked the output for that future tokens. Okay, so that's the masked attention that they did. So these three type of attention were there. Self attention, that's done in the encoder part. Cross attention, it happened between encoder and the decoder. Masked attention, that happened in the decoder part. Okay, yeah, and that's the end of week 9.
So this is done during training, right? Because during the inference, there's no need to do masking, right? Because you haven't seen really the future tokens.
Yeah, during the inference, you are just going to do the auto-regressive way that prediction of first word is going to feed as the input to the next token prediction. Okay. During the training, to make this entire task parallel, we want to do this computation. Because this was one of the bottleneck of RNN that we had. Even if we had the entire sentence in add already, we still have to do this task sequential just because of the structure that we had for RNN. And that was a big computation task because we did not take the leverage of having this entire sentence. Yeah. The next week we will be seeing the transformer model in more details. Okay, where we'll be using this attention mechanism, and then you will be seeing how the modern LLM works. Okay, of course not in full details, but we'll be starting reading about the modern LLMs like BERT, GPT-1, GPT-2, GPT-3 by OpenAI. Okay, and yeah, that's all for this week. Next week we won't be having any coding tasks. Just a reminder. Oh, okay, we won't be having any implementation because week 10 only had the theory about the transformer. Okay, the transformer architecture, then how the modern LLM thinks, like your GPT and the other transformer models. Okay, and
How
of
many
course,
weeks we have, Fulkit?
sorry,
How many weeks we have?
we will be having the full 12 weeks.
Okay. So
Okay,
NTT will be in which weekend?
not sure as of now that how many weeks will be there in the NPP, but I believe it will be by 8 or 9. Most likely, it will be before that. That's what I'm believing. But let's see.
So what type of model we should be training in that?
It's not uh, confirmed yet. Okay, maybe just wait for 2 3 days. Okay, things will get confirmed and we will tell you or update you. Okay. For now, the only update that we have, yeah, we have the score of your NPP. Okay, they are finalized. Most likely in a day or tomorrow, you will get your NPP one score. Okay. Along with that, we will be also releasing one discrepancy form. So if you feel or want to challenge your score that you have given less marking, then you can fill that form. We will again check it for you. Okay. Okay, guys. Final thing. So please fill this feedback form. Okay.
This quiz, some questions they ask up to 3 digits.
For the decimal.
Yes,
Yeah.
but
So
the answers are in 2 digits.
okay, the answers are in two digit. Then you can just put have zeros.
No, no, no. The answer and in the answer key they have given only 2 digits.
2 digit. Oh, okay. No problem in that.
Okay.
Uh, okay. Yeah, yeah, I saw that question. Enter the correct answer after 3 decimal. They have given it till 2 decimal. No worry in that. Okay. It will be handled. Don't worry. Okay. It's just that it's the range that they have given, right? So the range is given like 0.03 to 0.04.
Yes,
So
that's
even if
true.
you like answer like 0.31, then it is correct. 0.035, then also it is correct. So this is the range only.
No, 4, 3. Because 0.04 it has given us.
Yeah, so even if your like answer is 0.035, so it is still in the range, right?
3.5 is okay, but for me it's getting 4.03 to 0.04, but I am getting 0.043.
Okay, yeah, then it will be wrong because it is going out of the range. Okay, so only if it falls within the range, then it will be correct. Okay.
Three decimals, right? Three
Yeah.
decimal means 4 can be up to 4 to 0.04, 0.045, right? 4,
No, no, 0.045 is going out of the range that they've given. So the range they've given is 0.03 to 0.04. So anything in between can be correct. Okay. Okay. Yeah. Please fill the feedback form. Thank you all for joining. If you have any more doubts, you can ask. Else, okay. Yeah. Thank you all for joining. Good night, everyone. See you next
Thank you,
session.
sir. Good night.
Right.
Thank you, sir.
Thank you.